Most of us have an automatic washing machine in our home, and it's usually taken for granted. We expect it to start first time and provide excellent results without trouble time and time again. In fact, year in, year out. Water and chemicals are added to create a solution that, with agitation, frees soil from fabrics. But these solutions can also promote rust and corrosion, so the machine must be constructed from materials that won't rust or corrode. But the modern automatic washing machine is no ordinary product. It's really very complex. When we close the lid, mechanical and electrical components begin to work together in harmony, very much like an orchestra. This is the Simpson washing machine factory in Adelaide. We're going to see how washing machines are designed, built and marketed. Washing clothes has always been considered a drudgery, and machines have evolved to make the task easier. The tub meant you could use a stick to protect your hands. The barrel made it easier to agitate the clothes. Even today, the washing machine keeps changing. Due to electronics, the new gearboxes are smaller and more reliable.
Our latest research indicates that our customers want products that work very reliably, that will work day in, day out. They can set them and forget them, and they don't have to worry about them.
The company does market research and then has a series of meetings about how to modify the existing product lines.
Now, we showed this is one of the panels we showed, and most consumers thought that looked old-fashioned, very squared up, didn't really portray robustness or reliability, and one of the important issues that came out of the research, Pete, was the need for more smoother, curved, flowing lines.
Once the committee has decided, they issue a design brief to the design department.
Some of the important points is that we have to go for these round corners, okay? This lid, again, has to be metal. It's very important to convey a perception of solidity and quality through the metal lid.
I've just received the design brief for the washing machine project, and I'm now looking at some concepts here related to some nice clean shapes, easy clean. The brief called up for rounded corners. We've got a concept here which I've been looking at, which is based on a very soft sort of form. I think you can see here that as a general impression, this is sort of the way in which we're sort of moving this product away from square and sharp edges into something that has nice curves, easy to clean. The lid's totally integrated into the hob form. As you can see here, we've got a shape going on which is fairly pointed. That's just one of many ideas we've got. We quite like this one here because it sort of shows a general direction, and you'll notice here that a lot of these knobs and buttons fit in quite well into that panel, and also allows a room for a graphic to sit nicely in that panel, whereas this one here was a little bit off the top. This one again is a further development from the previous one. It runs off the top of the panel, and we don't have this hidden line, so it's a much more integrated look to the total panel. Flowing along from this, we need an electronic solution. We've got a couple of different ideas here for an insert that would fit into the total shape, which has a nice contoured feeling to it, and some push buttons for controls down here. We quite like this concept, however we felt that for various reasons it would probably work better in the opposite direction. And we've got an electronic panel here showing you this is a computer generated image which led on from one of these earlier concept sketches, and it shows you in more detail exactly what is on that panel.
Well, my role here is as an industrial designer, and on this particular project I was asked to come up with some concepts for the graphics and pick the colours and evaluate that.
Rebecca, we've got a sample here of a graphic very much in a blue colour here, which I'm wondering whether there's some other alternatives on here that we can look at. The timer here is very blue, as you can see, but I think we really do need to get a colour that's fairly neutral in most laundries, and bearing in mind the rest of the panel is pretty free of colour.
While this fine tuning is going on, the sketches are being turned into drawings.
My name is Ray. I'm a CAD operator with Simpson Email. I used to be a drafts draftsperson, which was producing drawings on the drawing board, old-fashioned drawing board. And the last 10 years we have changed to computers, and we are drawing now with our computer. It's slightly different in the fact that instead of producing a drawing first time, we have to produce what we term a model, which is a model of the part which we intend to draw. We create the model, and then from the model we can create our drawing, which is the opposite way to what we used to do it.
Sometimes the model is made by hand.
What we've got here is some early foam conceptual models which we have made for evaluation of shape. These models would generally be made after we've done a number of concept sketches and evaluated the shape that we rather liked. And what we're looking at here is a couple of different alternatives for what we can actually do in the control head area. You notice here there's something that's very round on the corners. We've got a model here which certainly conveys a very more square edge, but at the same time the control panel is very laid back. And the third one here is another alternative, a little bit similar to the first in terms of being very upright, but again it's a very squared up look.
Once a model is made, it can be scanned into the computer by rotating it in front of this laser beam. The laser measures the position of each point and gradually builds a model in the computer. Quite often, building a model means building it in the computer like this. This is the mixing chamber, and it's built up piece by piece, just as if you were building it out of balsa and glue. You work in wireframe, as it's called. Then, when you're ready, the model can be rendered in whatever view you choose. The computer program can now print out technical drawings from this 3D computer model. The computer file is ready to be sent off to the model maker to produce physical prototypes. The clear one is made of nylon on a laser sintering machine. The laser sintering machine reads the computer file, which has been sliced into very thin sections, 0.1 millimetres thick. Powdered nylon is rolled onto the bed in layers 0.1 millimetres thick. Then the computer, which is reading the plan of that layer, sends the 50-watt laser beam onto selected parts of the nylon powder and melts it. Then another layer of powder, and the next layer is produced by melting and cooling. As the layers build up, the shape changes and the model slowly grows. At this stage, the rest of the model is buried beneath in the powder. The laser traces out the pattern of a whistle, including the free moving ball inside. More layers, more lasered pattern, more powder. The loose powder is removed and the new plastic object remains. All these objects have been made by laser sintering. This whistle was made with a pea inside it. The powder was shaken out after the job was finished. These have been made with sand coated with a heat-setting resin. After sintering, it is placed in an oven to cure it fully. Then it can be used for casting molten metal. These were made in a modern version of the lost wax process. The original model is laser sintered from a low ash plastic. Then it's coated with sand and resin, heated to set the sand and vaporise the plastic. Then the molten metal is poured into the sand to produce a full-strength casting.
This is the Helicis LOM machine, or Laminated Object Manufacturing Machine. We start with a three-dimensional CAD model, which is in a format which can be sliced, similar to the selective laser sintering machines. We start with a resin-backed paper. You see this phenolic resin backing on the paper. The first layer is stuck down to the platform, and from then on, the paper feeds through. This roller here supplies heat and compression, travels across the bed and laminates the paper to the layer below. and then we have a 50 watt CO2 laser at the back there, and mirrors at 45-degree angles, and a focal tube with a focal lens, and this is just an XY plotter, and this just guides the laser beam around and cuts the profile of that slice through the part.
The paper not selected is cut into squares by the laser. It's chiselled out later. This manifold has been made in 2 parts, glued together once the waste has been removed. This spanner has been made all in one piece and works perfectly. Even a gearbox could be made this way. Another way of making a prototype is to send the CAD file to a milling machine. It then mills it out of plastic.
This here is a computer-generated model, 3D cut and Pro Engineer, showing you the basic form and shape of this new control panel. And we've done this to assess the total design before we take it any further.
These prototypes are expensive, so duplicate versions can be cast in a silicon rubber mould. The flexible mould allows objects, such as these buttons, to be cast with undercuts that could not be removed from a rigid mould. The pieces can be painted and assembled for publicity photographs and testing customer reaction. This model has been made in 3 pieces because these are the largest sizes the laser sintering machine could make.
And we check the fitment of all the parts that go into it. So if we have any modifications, we can do it on the run rather than wait for the tool and then have to do all the adjusting and modifying. It's all done before we even get the tool back.
If the prototype passes all these tests, then the tool makers begin working on solid steel blocks, producing the plastic injection moulding tool. Again, the milling machine is controlled by the same CAD file. The moulds have to withstand up to 1,000 tonnes, so they're very thick and very heavy. They're also very expensive. The mould is placed in this press, and the polypropylene plastic is injected into the space between the 2 parts of the mould. Once out of the mould, the risers and the sharp edges are trimmed off. The parts then go to the assembly line, where they're fitted in place. The assemblers wear gloves to protect their skin. Any plastic enclosing electrical wires must be flame retardant and have low electrical tracking characteristics. That is, sparks must not be able to run along the surface of the plastic. After assembly, all panels and wiring are checked to make sure everything is working correctly. This shows what the agitator would be doing. The top panels aren't made of polypropylene because it can't be glued, so high-density polystyrene is used. The gearbox housing starts as molten aluminium. A special marine-grade alloy is used to resist the alkaline washing solutions that would corrode normal aluminium. The molten aluminium is ladled into the machine. The ram then forces the metal into the water-cooled mould and stays there long enough to solidify. The castings will be trimmed before use and the runners will be recycled. Here we see cabinets for dryers being folded. The steel is cold rolled steel with a zinc and aluminium coating called Zincalume. It comes painted and can be folded. Washing machine cabinets are wet products and must be more rust resistant. They are electroplated with zinc, then rolled smooth. The galvanised steel is stamped to shape before painting. Painting after forming prevents micro cracks and produces superior scratch and corrosion resistance. With presses, there's always the horrifying possibility of cutting off an operator's hand. So to make sure this can't happen, there are safety guards, and as well, 2 buttons need to be pressed at the same time. This makes sure that both hands are out of the way when the press comes down. The switches are also covered to make sure they're not accidentally triggered. With 2 operators, all 4 hands have to be on buttons before the press will operate. After stamping, panels are powder coated with a special powdered paint. This gives a thick resistant coating. When the panels are baked at 200 degrees Celsius, the paint sets to a surface that's extremely tough and chip resistant. As in the rest of the factory, all the panels are inspected before going on to the next stage. The challenge in manufacturing is to make high-quality items cheaply and safely. To reduce back damage, the cabinet is tilted towards the person to reduce stretching and back fatigue. In the old days, jobs such as repeatedly turning a screwdriver could lead to repetitive strain injuries. Nowadays, this job is mechanised. It's faster, easier, and the results are more uniform. The gearbox is the heart of the machine. The gears are both steel and acetyl plastic with 5% fiberglass. This combination gives quiet operation. This shaper is cutting splines on the stainless steel drive shaft. It's impossible to see from just looking, but these have been cut with extreme accuracy. The gearbox is sealed for life, being designed to work for at least 20 years. Nowadays, people work in small teams and work in more circular workplaces. People are happier and much more efficient. Where a straight conveyor belt is still the best solution, people have a stop switch nearby so they can stop the line if they can't keep up or suspect something is wrong with the quality.
We like them to rotate every 2 hours. Some of the guys like to do it every hour, which we don't have a problem with. It saves a lot of problems quality-wise. It saves a lot of health and safety problems. We don't get as many back or hand problems. It makes it easier on the guys here because we're such a small group. They can rotate and learn all the different jobs. They're not staying on one job all the time.
One of Maureen's jobs is to make sure everyone has the right training to be able to do the job efficiently without stress or error. It's important that every operator has training off the job, where they can concentrate on learning without the pressure of production.
So that your wires are nice.
Here a stainless steel sheet is being rolled up to produce the mirror finish spin bowl. All joints are crimped, as welding can lead to corrosion problems. The outer bowl of the washing machine is made in one piece in the plastic injection moulding machine. All parts in contact with water are made of stainless steel or polypropylene. the same plastic used to hold the acid in car batteries. This plug is welded in place by spinning it until it becomes hot and molten, then letting it cool and bond. The mixing chamber we saw on the CAD drawing cannot be moulded in one piece, so it's heat welded together. Each piece is melted by hot Teflon coated surfaces, then held together until it cools solid. The operator then examines the work before it proceeds to the next stage. Robots can be used to trim complicated mouldings. The bowls travel by conveyor to the assembly point in the factory next door. Any not used return to the source and go around again. The overhead conveyor acts as additional storage. When they're needed, the bowls are taken from the conveyor. The motors are bolted in place while the bowls are upside down. To help prevent back injury, a crane is used where possible. Factories are noisy places, so the washing machine goes into a special soundproofed room where the tester can check to ensure everything sounds right. In the test laundry, the machines from the production line and the new test models are run through their paces to see how well they wash, rinse and spin dry. These are typical test loads. To test washing, standard dirty swatches are pinned to the load and run through a wash cycle. These standard laboratory fabric test samples have been soaked in a secret mixture of muck by an independent laboratory.
We put in our soil swatch that we have here into the reflectometer. We get a reading of 47.5 of the soiled swatch. We'll then attach that soil swatch to our clothes and go through a washing test. Once the swatch has been washed, it will come up whiter. We'll remeasure that swatch. Comes up with a soil removal of 80.
Many things need to be tested, such as different detergents, water temperatures, spin and rinse efficiencies. Of course, cleaning isn't the only criterion. A cement mixer or a bash on a rock may give a good result, but it would be hell on the clothes. The washing machine has to provide a balance between gentleness and soil removal. These test swatches are made to be easily frayed. They are pinned to a standard wash, then measured after washing to see how many strands may be missing. In the industrial design section, the look of the machine is created, whereas here in the engineering section, the mechanics are developed. Serge is working on the braking system.
What you're seeing here is a transmission system that's energised the little brake clutch solenoid. It's allowed the clutch system to be disengaged, and the machine is now spinning as it would in a spin cycle. By lifting the lid, we're actually going to de-energise the brake solenoid, allow the brake levers to come into contact with the brake tongue and lock the system into a brake mode.
Of course, if you change one thing, such as a brake, the whole machine has to be tested to ensure that other problems don't occur. For example, can the suspension rods take the forces?
Thank you.